All right, I think we'll get started. So hello everyone, my name is Matt Sandy. I'm a program manager on the Direct3D team at Microsoft, and I'm here to tell you about a really cool new feature that we've created in DirectX called tiled resources. And now one of the coolest things about this feature is that unlike some of the other cutting edge features that we've released in the past, at launch, tiled resources will be supported on next-gen console and many of the DirectX 11 PCs already in the field. So that's just some context for what you're about to hear today. So for today's talk, I'm going to go over a few things. First, I'm going to tell you about a challenge that many games today face, and that is the problem with textures. Next, I'm going to tell you about some existing solutions to this problem. Then I'll tell you about how tiled resources solves these problems in a more efficient manner. And finally, I'll show you some cool demos to take advantage of it. So what is the problem with textures? Well, it's not so much a problem with textures as it is a challenge that games have with ever-increasing gamer expectations. Take this screenshot, for example. Gamers today want expansive, massive worlds with very little data repetition. So, for example, in this scene, gamers are going to want to be able to explore every part of this world. So take this house in the bottom of the screen here. If you're going to want to allow players to explore this house up close, you're going to need about 10 megabytes of texture data to add enough detail to make it realistic. Now take this vehicle, which is going to be the player's main point of view for the entire game. You're going to want that to be ultra-high detail because they're going to be looking at it for the entire game. So you're going to need on the order of about 100 megabytes for that texture. Now if you look in the right-hand side of the screen, you got this town in the distance. Now if you want that town to be able to be explorable by the player, you're going to need unique houses for that entire town and lots of texture data, probably on the order of about a gigabyte. And finally, you have the terrain. If you have miles and miles of expansive terrain, all with unique areas, fully explorable, you're going to need a ton of data for that, probably on the order of about 10 gigabytes. Now, obviously, this ratios will vary from game to game, and in particular from genre to genre, but typically the overall totals for textures are about the same from game to game. And just to give you another view of what this looks like for actual gamers, this is a screenshot of my hard drive before I've installed the latest AAA first-person shooter. And this is what my hard drive looks like after. So what goes into that 23 gigs that just got burned on my hard drive? Well, in reality, the majority of that is actually textures, and the rest is everything else. Meanwhile, this is how big my GPU is. So obviously, you can't fit all 10 plus gigs of textures into video memory at the same time. So that's really the problem with textures, is that your GPU is typically smaller than your total asset size. But obviously, games solve this today. And that's solved by the observation that typically only a very small fraction of this data is needed to render a given frame. In fact, for a 1080p display, you only have about 2 million pixels to light up, which means you only need about on the order of 2 megatexels. The challenge is getting the right texels onto the GPU at the right time. So let's review some existing solutions to this problem. So one of the most common solutions to this problem is a solution called texture streaming. This is a solution where a game will stream textures as needed based on the player's region, their viewpoint, and typically an LOD management system. So as you get closer to an object, the management system will load in more and more detail as needed. And as you move farther away from the object, it will unload those resources, making room for more high detail resources. Now, this typically works well enough in theory and in practice, but there are some limitations. For example, with texture streaming, the stream granularity is still on the order of whole resources, which are still typically around 10 megabytes. Meanwhile, your PCIe bus bandwidth, given a 60 frame per second game, only gives you about 85 megabytes per frame to stream data. And assuming you actually want to do some rendering during this time, you have significantly less. Now what this means is if you have a game with lots of variation, or you have a lot of data being streamed in and out, you may need to introduce artificial transition regions, such as long bridges or long elevators, so that you can stream on and off the data that you need without glitching. Also, texture streaming has a lot of overhead. For example, because you can only stream in units of sub-resources, if you, say, for example, go around a corner and you encounter a table, a long table with a single texture, the area of the table very close to the player is going to need to be very high detail, whereas the region further away, you don't need that much detail. Because it's all one texture, you have to load the entire thing, even if you're not using it. So software tiling is another approach to this problem, and it improves on texture streaming quite a bit. Instead of streaming entire textures, software tiling breaks up textures into small regions called tiles. And instead of streaming entire resources, it will stream individual tiles as needed. Now, with software tiling, the indirection lookup is done in a pixel shader with a secondary texture. So I'll explain how software tiling works now. So on the left, we have our lookup texture, which is, instead of a texture representing actual color data, it represents metadata that says, given a given textile coordinate, where do I go to a secondary texture to actually find the real color data? So here, if we're going to sample from this red dot, Q, the lookup texture will say, look in the data texture at this other point, and then the pixel shader will actually load those data samples and potentially interpolate them if necessary. So this works well enough for bilinear filtering because you don't actually have to do any manual filtering yourself, because typically you can do a bilinear stamp in the data texture. Once you get to trilinear filtering, though, you do have to do a linear interpolation between the two MIP levels, potentially. And things just get messier as you get into anisotropic filtering, because you have so many more sample taps to worry about. So in addition to these other issues, in order to avoid seams at the tile boundaries in the physical data layer, you have to duplicate your tile data with border regions. This is necessary because, given a particular sample location, a given filter will potentially sample from multiple locations within a particular region of the original sample point. What this means is that even if you translated a particular logical location to the physical data location, if your sample expands off the border of that particular tile, your adjacent tile is not going to contain the right data, which means you need to potentially pad out your tiles however far is needed to cover the maximum width of your sample taps. What this means is that with larger formats and higher anisotropic counts, you're going to need a wider border, which means more memory overhead. Now this graph illustrates this effect. As you can see, with higher bit depth formats and with higher anisotropy, your overhead increases dramatically. Now, just to highlight a particular data point for you, which is a common one in games, 4x anisotropic filtering with 32 bits per pixel texture format will have approximately 10% or higher border overhead. So overview of software tiling is that it does require manual filtering, anisotropic filtering is complicated, and you have to have some extra memory overhead in order to duplicate data in your data texture. So wouldn't it be nice if we didn't have any of these limitations and it was just supported in hardware? Well, now it is. With hardware tiling, it's basically the same approach for software developers as software tiling, except for by using a hardware programmable page table, you don't have to have your own lookup texture, and therefore you don't have to have border regions as well. So let's take a look at how hardware tiling works. So on the left, we have a virtual texture in logical space. Now this is broken up into individual tiles as software tiling is. But instead of having this represent a lookup texture, instead, we have an actual page table in hardware that says for every given location in the logical texture, where can that data be found in the physical memory? Likewise, corresponding to this page table, we actually have our physical memory, which actually is the real data that's stored in the texture. And because of the location of the hardware filtering units, because the filtering units are before the page table in the hierarchy, when you sample from a given location, even though a particular filter kernel may span multiple different data points, all those data points are uniquely and individually translated by the page table, so they all go to their correct addresses in physical memory, instead of having to pad out your data or do some extra math to figure out where you need to go. The result is that bilinear, trilinear, and anisotropic filtering are all equally simple. So a quick overview of hardware tiling versus software tiling is that you can use regular sampling. You get anisotropic filtering for free. You don't have to have border regions. And because the page table is in hardware, you don't have to have an indirection texture to look up data first. So now let's talk about hardware tiling's exposure in DirectX, which is tiled resources. So first, I'm going to go over some key API concepts of tiled resources. The first is the tile pool. Now this is a buffer object of 64 kilobyte physical tiles, and this represents the physical memory of the GPU. Likewise, the tiled resource is either a Texture2D or a buffer object that you've created with the tiled flag. Creating it with the tiled flag indicates that instead of, as you normally would, allocating video memory for the entire surface, you're only reserving virtual address space. And in fact, you're not actually taking up any physical memory for the page table yet until you start to map tiles. Likewise, we've added APIs for many common scenarios, such as update and copy tile mappings, which are used for programming the page tables. We've also added update and copy tiles APIs for easily getting data to and from physical tiles. We also allow you to resize the tile pool. And another interesting API we've introduced as part of tiled resources is the dependency barrier. Now, this is required with tiled resources because although the Direct3D runtime will traditionally track hazards for you to make sure that you're not creating data races, tiled resources introduces the potential for a new kind of data race, where although two resources may appear to be totally independent, if they are both backed by the same physical data, then you have the potential for a race condition there. So by adding the tiled resource dependency barrier API, we allow you to specify where you have data races that are not going to be detected by the Direct3D runtime, so that you can allow the Direct3D runtime to enforce those dependencies for you. So let's go over a quick scenario for how you would use tiled resources in a typical application. Well, first what you need to do is to create the tile pool. You do this using the create buffer API, but using the new flag, which is the D311 buffer MISC tile pool. This creates physical memory backing for our logical tiled resources. And as I mentioned before, you do have the ability to resize the tile pool at any point in time. If you find yourself getting under memory pressure, or if you find yourself not needing that much memory, you can reduce the size as well. So once we've created our tile pool, we need to create our actual tiled resource. So here we call create Texture2D with the D311 resource MISC tiled flag. What this does is it allocates virtual address space for the tiled resource and also allocates some space for the page table. Now, as I mentioned before, when you originally create the tiled resource, these page table entries don't actually take up that much space. In fact, the total size of the page table usage is going to be proportional to the number of tiles you have mapped. So something to note, when you first create the Texture2D with tiled flag, all logical tiles are by default null mapped, which means they have no physical memory backing. So in order to back the logical resource with physical memory, we have to program the page table. And we do this using the update tile mappings API. Now, this is an extremely powerful and robust API. In fact, given any existing mapping and any target mapping, you can always produce a single call to update tile mappings to cause the tile mappings to change to what you want. So in this example, we're using two different ways of specifying tile regions in the same call to update the tiled Texture2D to allocate space in the physical tile pool for it. So here we're going to map box A through F to physical tiles starting at location 5. So that's going to map A, B, E, and F to 5, 6, 7, and 8 physical tiles. Likewise, we can also specify a linear range of tiles, for example, L through N, where we're mapping L, M, and N to physical tiles 0, 1, and 2. So once we've done update tile mappings and we programmed our page table, we can start putting data in the tiled resource. And we do this by calling the update tiles API. So here, for example, we're using the same box definition for a region, and we're going to update this with an example blue gradient data. This will use the page table to figure out where in physical memory this data needs to go, and it will stream the data through the tiled resource to the tile pool and update tiles A, B, E, and F. Likewise, we can call update tiles on the linear region with some other gradient data, L, M, and N. Now, an important thing to note is that the existing update and copy APIs work just as well, but those are pixel-based, so if you're dealing with updating specific and individual tiles at the tile granularity, it makes it much easier by using the update tiles API because you don't have to worry about pixel borders and aligning them to tile boundaries. So once we've created our tiled resource, how do you go about using it? One of the great things about tiled resources is that it's just a normal texture now. You can sample in shaders, and in fact, you can use your existing shader code. What this means is that you can incrementally adopt tiled resources without, for example, needing to update your entire shader codebase. But if you want to, tiled resources also comes with some new instructions as well. For example, we've added a new sample overload that samples with feedback. And what this sample operation does is instead of a normal sample, it additionally returns to you a feedback result, which tells you whether or not the sample operation sampled from a null map tile. This is useful for debugging your residency management system, for example. We have also added a clamped sample instruction. What this allows you to do is it allows you to specify a minimum level of detail to a sample operation. And instead of, for example, the behavior of sample level, which ensures that all samples sample from a particular LOD, sample with the clamped filter, what this does is it causes every individual sample point to be clamped to a particular minimum value. What this means is that if you were going to sample from a location that's higher than the value that you clamped, less detailed, it will sample normally. But if you happen to sample from a location where the typical LOD system would calculate a more detailed level than you specified for the clamp, it will clamp those samples to that LOD, ensuring that you don't accidentally sample from a more detailed MIP level than maybe you have made resident. We've also added some new filter variants, such as minimum and maximum. What these do is instead of the standard sample operation, which does a linear interpolation of each sample point, it actually returns the minimum or maximum value, respectively, of each of those sample points. Now, this is useful in the context of the clamp instruction, because what you can do is you can have a resource that actually represents the minimum LOD level for every location in the tiled resource, so basically one texel per tile. And then by using the maximum filter, you can actually figure out what is the maximum level of detail resident within the radius of a particular sample kernel. And then by passing that to the clamp value, you can guarantee that all of your sample operations on your tiled resource will return resident data. So now a quick digression to talk about tile shapes. I have mentioned throughout the talk the concept of 64 kilobyte tile size. But how does this actually map to individual texels? Well, that depends on MSAA count and the texel width, so in bits per pixel. It's actually, you can memorize this table, but it's actually pretty easy to remember. Basically, for at 1x MSAA, you take the bit per pixel count, see if you can create a perfect square in 64 kilobytes. If you can't, try and create a double wide square, and that's your standard tile shape. And for 4x MSAA, just divide the width and height by 2. So now that you know how tiled resources on DirectX works, I'm going to show you a demo that takes advantage of it. So you may recognize this demo from this morning's keynote, but let's take this opportunity to explain a little bit more in depth about what's actually going on here. So here we're rendering a 3D representation of the surface of Mars using 3 gigabytes of real NASA data. Now in the bottom right, we actually have a visualization of the residency map for this tiled texture cube. In this example, we're using a 16K by 16K texture cube for both a diffuse and a normal layer. So this is a lot of texel data that's being streamed on. And in fact, we're only using a 16 megabyte tile pool. So we're really pushing the residency management system to its limits. As you can see, from a particular depth, we have many, many tiles, as shown in the visualization, that have a moderate level of detail resident. But as we zoom in, we see that the central region becomes deeper and deeper blue, while the other regions outside the camera become more green. This is indicating that areas central to the camera are getting much higher detail residency, whereas areas outside the camera are being evicted, so they only have low detail residency. And as we zoom in close to the maximum level of detail, we see almost a single point of very deep blue, indicating the maximum level of residency for detail. Now we can actually do a visualization of what tiles are being streamed in from what MIP levels by turning on colorization for tile borders. So here we see the outline of each individual tile, where the color represents what MIP level that tile is coming from, where magenta is the most detailed MIP level, cycling through blue, green, and eventually yellow. Now, the reason that these are wide tiles is because the diffuse color here is BC1, which is one of the non-square formats, that's why the tiles don't appear square. And just to recap this morning's demo, as we zoom out here, we get to the yellow MIP level. And if we were to actually take that same 16 megabyte tile pool and allocate that detail evenly across the entire cube map, which we can emulate by clamping the level of detail, This is the level of detail you'd get. You really wouldn't go any further than the yellow MIP level. But by turning on tiled resources, we can get all the way back to the magenta MIP level, just in those same 16 megabytes. So just a quick recap of the demo. The demo had two 16,384 by 16,384 tiled texture cubes with two layers, one of them diffuse BC1 UNorm format, and one of them a normal layer, BC5 SNorm format, totaling 3 gigabytes of total source data. Meanwhile, the tile pool is only 16 megabytes shared between the diffuse and normal layer. That's less than 1% of the total assets. So how did we get to 16 megabytes? Was it just trial and error, or was it calculated? Well, actually, there is a rough equation you can use when using an approach like this for tiled resources for picking a minimum tile pool size, or at least the minimum that you could possibly need to render a scene. It's actually, interestingly, proportional to both your display size and the various formats you're using for layers in your image. So take, for example, in the demo. The demo was targeting a 1080p display, so 1920 times 1080. We had two layers. One of them was 4 bits per pixel. One of them was 8 bits per pixel. And then we have this multiplier, 4 times 1.33, which I'll explain later. But that gets us to 16 megabytes. Now, where do the 4 and the 1.33 come from? Well, that's due to MIP levels. So for a given image, for a given frame on the scene, let's assume that you have a 1-to-1 pixel-to-texel ratio, which means you're exactly sampling 1 texel for every pixel on the screen. Now, if you zoom in the camera a little bit closer, every pixel is actually going to sample from 4 texels at the next detailed MIP. So that's where the 4x comes from. In addition, the sample also employs the technique of having every less detailed MIP level always resident, given a particular MIP level's residency. So, for example, if you have MIP level n resident, then all MIP levels less than n are also resident. This ensures that there are no holes in your MIP pyramid, which tends to make residency management easier. So let's talk about some usage examples for tiled resources. So one of the most straightforward ways you can adopt tiled resources is in your terrain system. So this is the example used in the Mars demo. Your terrain layers can be 16,384 by 16,384. You can stream in tiles as needed based on the player view or based on game events. For example, if you know that you're going to be leaving a building, you can preload the tiles for the terrain outside the building. But there are some other examples as well of great uses of tiled resources. One of these is for shadow mappings. So shadow buffers tend to consume a lot of video memory. But by using tiled resources, we can actually make much better use of that same memory that's allocated for the shadow buffer to produce much higher quality shadows. And now I've got an example to show you of that technique. So in the demo I'm about to show you, provided by NVIDIA, we were actually allocating a 16K by 16K, that's 16,384 squared size shadow buffer. And by allocating only a 16 meg tile pool, we're actually able to do this in a very small amount of memory. I'll bring this up here. So this is an example of the scene without tiled resources. So with the 16 megabytes that we're going to use for the tile pool, this is the quality that you get with those same 16 megabytes with a uniform detail density. Shadows look okay, but you get a lot of shimmering and it looks kind of weird. So let's apply those same 16 megabytes to a tiled resource for the shadow buffer. As you can see, by applying those same 16 megabytes to the detail areas that are needed, we get much crisper, clean shadows. So some other great examples of use cases for tiled resources are atlasing. So one of the main use cases for atlasing is to actually reduce your memory footprint. And typically what this means is that you need to pack in your data as close as you can within a particular texture so you can reduce the overall width and height of the total texture. But by using tiled resources, if you have regions that are, for example, don't have any data in them, instead of having that data actually mapped in it as a texture, by creating that as a tiled resource, you can leave those tiles unmapped, which means they don't take up any physical memory at all. And there are many other examples of tiled resources. Image editors, map viewers, any system where you're operating on lots and lots of data and need a visualizer or to do arithmetic or calculations on it, computation in general, tiled resources is going to be a huge win. Now, a quick note on residency management. This is really important to note that residency management is going to be the key in taking full advantage of tiled resources. This is because the better your residency management system is, the better advantage you'll be able to take of the technology. So just some ideas to get you started for texture or for residency management. You can use dedicated low-resolution sampling paths. So this is the technique employed in the Mars demo. Basically, you do a low-resolution pass, which instead of encoding color data, actually encodes the texture coordinates as well as the MIP level. You can then read that data back and feed that into your residency management system. Or if you already have a deferred rendering system, you can incorporate that same approach into that rendering pass so that you can, in addition to encoding data about the general gbuffer properties, you can also encode data about the MIP levels that need to be loaded, for example, for this or for future frames. Naturally, you can use game-specific state knowledge, as I mentioned before. If you know a player is going to be exiting a building in the next few frames, you can preload that data. Or if you already have an existing LOD management system, for example, if you're already using texture streaming, you can incrementally adopt tiled resources by, instead of limiting your LOD system to streaming in and out at the sub-resource granularity, you can stream in and out at the tile granularity. Another approach you can use is to use middleware. And so now I'll bring up Charles Holomersch from Graphine Software, who will tell you about their middleware that they've created that's actually, they've updated to use tiled resources.
Yep.
Charles?
Thanks. Yeah, I'm Charles Holomersch, and I'm a co-founder and CTO of Graphine Software. And with the founding team of Graphine, we've been working on texture streaming for a very long time, so we're really very excited to finally see the texture streaming and the tiling technology find its way into the graphics hardware and, of course, into the DirectX API. So I'll tell you a bit more about our product. So our product is a middleware solution for game developers, or for any sort of real-time 3D applications. And it's basically a software library that you integrate into your game. And by using our library, you get rid of a lot of the kind of low-level details of the tiled resources API, and in particular the residency management. But I'll start with a demo. It's still running the NVIDIA. In the demo, you'll see. So the demo was actually shown this morning on the keynote. And so what you're seeing here are the planes. The first thing you should notice are the planes. They are 8,000 by 8,000 pixels for a single plane texture, and we actually have 4 of those. And so, in addition to just the color information for the plane, so the diffuse texture, we also have 3 additional layers. So we have the normal map, we have the specular map, and we have a roughness map. And so in total, if you look at the planes uncompressed, they would be around 4 gigabytes of data. So if you look at raw RGBA pixel data, the planes alone are 4 gigabytes. And in addition to the planes, we also have the landscape in this demo, and the landscape is using 64,000 by 64,000 pixels of texture data. And for the landscape, we have a diffuse map and a normal map. And so again, if you look at the landscape in a raw pixel data fashion, then it would be 32 gigabytes of memory. So in total, we have 36 gigabytes of raw data, which is being used in this demo. Obviously, you can't really use all that data or load all that data, so that's where tiled resources comes in. So what is really the kind of key things that you have to make sure when you try and use tiled resources? So the first thing is that you minimize the latency. So that's the path from the tiles stored on your disk all the way into the memory, into the GPU memory. You really have to shorten that path as much as possible, because all the clever tricks you do, you still have to load the data as fast as possible. So there's really no excuse for that. And also, by really minimizing the latency, you can really reduce your cache size. Like as Matt said, that way you can get away with showing a lot of data with just 16 megabytes of physical memory behind that. So that's also really a key thing. And another thing which then is more inside the Granite library, that's minimizing the storage size. Because if you have a raw data of 36 gigabytes, there's no way you can get that game shipped to your gamer, because you're going to have more than just one level. So that's just way too big. So what we do is we have a custom compression API, and that kind of that works not only for the diffuse but also for all the typical game formats, like for normal maps and all these sort of things. And in case of the demo, like it's a high quality setting, we get the data down to about 3.5 gigabytes. So that's already a lot more manageable to distribute. And finally, of course, we also have a whole set of tools, and we make our library really easy to integrate into your existing engine, so that way the production overhead of adopting tiled resources can really be reduced. So in a way, with Granite, you can just maximize your unique texture data and stop worrying about it. So let me just skip over these. This gives a more architectural overview of our library. So on the right-hand side, you see the backend. So this is basically an abstraction layer on top of the graphics API, and so that's where we address the tiled resources API. And then on the left-hand side, you have the streaming core. And so the most important part of the streaming core, that's the streaming runtime. And so the runtime works similar to when you have virtual memory on a CPU, and you do a memory load instruction. So the CPU goes to the page table and then fetches the correct value from physical memory and returns that to your program. But in case you have a miss, then the CPU will generate an interrupt, and then the operating system kicks in, and it will load a page from the swap file, and possibly it will decide which pages to evict from the physical memory to make place for the new page. So, and in a similar kind of way, the streaming runtime takes care of all of that. So it makes sure that the pages are loaded, and it does that asynchronously through multi-threading. And then also it decides which pages should stay in memory or which pages should get thrown out. And of course, this closely works together with the residency analysis, because contrary to the CPU side, you don't get an interrupt, or the GPU doesn't get interrupted whenever it does a lookup to a page which isn't mapped. You just get a default caller or something. So you have to actually predict which tiles can be possibly accessed by the GPU for a given filtering mode and a given texture. And so this is where the residency analysis kicks in, where you kind of predict which tiles the runtime should actually load to the physical memory. And then another component, that's the compression and decompression, because on disk, you really want to store your tiles in a highly compressed format. Not like even the BC, the BC1 or BC5 block compression formats, they are still too big to be stored on disk. So you really want to transcode the data from the disk format into a GPU-friendly format, and that's quite a demanding step. So you want to optimize that quite a lot. And at the bottom, then we have some tools that really generate the page file. And so the page file we optimize it based on the disk layout, so it works with the physical sectors of the disk. And that way you really can make sure to really shorten that latency and make uploading tiles very fast. So yeah, of course, we adapted, we had an existing library, so we adapted it to the tiled resources, and now I'm going to discuss our experiences with that in a bit more detail. So the first thing that we had to tackle, of course, was predicting the tile residency. And here we use a similar system, like our software-based system, and like Matt just described. So where where we render an extra pass, and then we analyze the output of that pass to decide which tiles are resonant. Different from a software system is that you have to actually load more than one tile. You have to load your whole MIP chain. So yeah. Another thing that the hardware doesn't take care of, and that's different compared to either a software system where you kind of get this for free, or even the very old systems that existed, is that there is no automatic fallback to a lower MIP level. So if you sample a level at a certain resolution and that resolution hasn't been loaded yet, you have to take care of handling that case. Because even if you have really good prediction, even if your analysis of the scene was perfect, data is probably not going to be available sometimes because the disk is slow. So you aren't guaranteed that all your data is available in the tiled resource. So the developer has to handle this, and in our case, in the island demo, we handle this by using an extra texture. And so the texture contains, for every region in the tiled resource, it contains the highest resolution level we have got available. And then we use a clamping instruction like Matt described. They have added clamping instructions to the HLSL. And so we clamp or texture lookup into the tiled resource based on the output of the auxiliary texture we use. And so that way we are sure that we're never going to sample any data which isn't resident. And so, because if you would do that, you would just get some black, or it would fade to black because it's doing true linear filtering or something. Another interesting thing is that the maximum surface size of the resources hasn't increased, so that's still 16,000 by 16,000 pixels. This is because, like Matt said, the filtering is happening before the virtual memory translation. So, and the 16,000 by 16,000 limit is actually caused by the filtering unit, because the filtering unit has to guarantee 8 bits of subpixel precision to the shader. And so this value didn't actually increase because the filtering unit hasn't changed. So, but this doesn't stop you from allocating really large resources. But for example, you have to allocate them through a different way. So you can allocate them as cube maps, or you can allocate them as array textures, and then store your data as some sort of larger meta tiles inside an array texture. And so, for example, in the demo I've shown you, we really do allocate 16 gigabytes of virtual memory. Of course, a very small portion of that memory is mapped, but virtually it's really 36 gigabytes for just one, 16 gigabytes for just one DirectX resource. And at the borders of the meta tiles, you maybe have to do some clever tricks, but probably that's a case which is not really going to occur very often. So yeah, this is of course the really interesting bit, the benefits of tiled resources. We didn't have access to the drivers for a long enough time to really do very detailed measurements like instruction cycle counts or anything like that, but still we have some quite promising results already. So as Matt said, we don't have to do any overlapping borders anymore. So this saves us around 20% of memory in the case of 4x anisotropic memory. And also, there is no need to generate mipmaps for every tile anymore, because if you want to do trilinear filtering in a software implementation, you have to generate a mipmap for every tile you load. So this actually saves you another 20% of cache memory, because you don't have to load a single mipmap, the first mipmap anymore. And so in addition to just not saving the memory, it also increases the streaming throughput, because as I said, we upload our data as a block compressed format, but it's coming from a different format. So, and transcoding this is quite a complex operation. Even if we have optimized it with all the SSE and everything, it's still quite a bottleneck. So saving another 25% there, it's really a big gain. And finally, of course, the shader gets a lot simpler. So our software implementation, which has 4x anisotropic filtering, uses 28 operations, and so in case of hardware virtual texturing, even with the trick I described, where we use an extra indirection texture to make sure that the level gets clamped to the highest resonant one, even with that trick, we still only need 11 operations to do a texture lookup. So that's a really big gain. It's almost a third of the shader instructions. So there's definitely, we haven't done any very detailed measurements, but this is definitely going to be a win in a real life shader. So yeah, the takeaway from my part of the talk is that tiled resources, they expose the underlying hardware virtual memory, and this makes all your sampling shaders a lot easier compared to a software implementation or a shader-based implementation. And so our product Granite kind of sits on top of the hardware offered, and it's basically like an operating system for virtual texture. So it takes care of loading the texture, paging the texture, and then deciding what should stay and what should go out. And of course, in addition to this, we have tools that allow you to make the page files, the file it's swapping from, which is compressed on disk. So yeah, so we'll be uploading more detailed information about our performance experience to our website. So we'll try and really measure this in more detail. So yeah, you should check our website for an update on that. And for the gamers in the room, we're also having we're also giving away 10 copies of Dragon Commander. Dragon Commander is a game by Larian Studios, and it's using our texture streaming library. So if you retweet or talk announcement, then you'll be eligible to win one of the 10 copies. So these be Steam keys, so it's really easy to get one. And we'll be around for the next couple of days. So if you're interested, or if you just want to discuss the tiled resources API, you can always come and talk to us. I'll give the floor back to Matt, who's going to wrap up the talk.
Thanks, Charles. So quick recap of tiled resources. Problem with textures is that gamers want ever-expanding worlds, and this requires correspondingly massive amounts of texture data. By exposing hardware programmable page tables, DirectX tiled resources allows game developers to make better use of memory, which means more detailed games and better games for gamers. So here's how you start using tiled resources. You can go pick up the Windows 8.1 preview here. You can have some other links as well to the Visual Studio 2013 preview, which includes the 8.1 SDK. I'm also going to be posting the demo code to the Mars demo, as well as some additional resources. Those links are not live yet, but they will be shortly after build. And check out Graphine Software at their website. And these slides will be available online as well. So thanks. I'll take questions. back to for questions. Yeah. Any questions? Yeah. So yes, there are some libraries for OpenGL as well. Tiled Resources is a pretty great solution as well, though, mainly because Tiled Resources, like I mentioned at the beginning of the talk, has broad hardware support at launch. So this is cross-vendor, cross-platform, obviously, next-gen console. So there's a really huge support base already right out the door with Tiled Resources. Any other questions? Yeah. For Windows 8.1, this is only Texture 2D and the family of Texture 2D, so Texture 2D, Texture 2D Array, and also buffer objects. So Texture 1D and Texture Cube, you can't, or Texture 1D and Texture 3D, you can't use with Tiled Resources. Yeah. Yeah. No, this is DirectX, which is part of the platform. So desktop, Windows Store, doesn't make a difference. It's available in both. Okay. Thanks. We'll be here for a few minutes after the talk. You can come talk to us. Thanks for watching.